Okay, welcome back. So let's just summarize where we are. So we want to prove this theorem that if n is greater or equal than 2 and m and 0 sitting in Rn plus 1 is uniformly convex, which means in particular that all the principal curvatures are positive and uniformly positive with respect to the mean curvature. This can actually be dropped, but I want to formulate the things that are technically used in the proof. Weak convexity is enough because by the maximum principle after a short time you would get this inequality for some such epsilon. Then the solution of the curvature flow contracts to a point in finite time and becomes more round, which means that after rescaling appropriately, the solution converges to a sphere. And we had shown so far that this estimate is preserved. And we were in the process of proving a key a priori estimate that there exists a sigma positive and a C1 depending on the epsilon, the initial surface, such that the trace-free part of the second fundamental form, so this is a squared minus 1 on nh squared, is less than this constant times h to the 2 minus sigma, meaning that the trace-free part becomes very small compared to the mean curvature as mean curvature goes to infinity. And we had already shown with the help of a Poincare inequality and the evolution equation of the quotient of this term divided by h to the 2 minus sigma, that the LP norm of the quotient satisfies an estimate. So f sigma, which was a0 squared divided by h to the 2 minus sigma, satisfies an estimate that the integral of f sigma to the p d mu to the 1 on p is less than a fixed constant C2, depending only on the initial data, in particular, of course, depending on this epsilon here, provided sigma is small and p is large, but sigma is not too small compared to p. So p has to be large, so this is 100 epsilon to the minus 2, and sigma has to be less than n over 8 times epsilon cubed times p to the minus 1/2, and the key point here is that as p tends to infinity, this is a power which is less in absolute value than 1. So 0 minus 0.9 would have been fine as well, but we have to be somewhat larger than p to the minus 1. So this is what we proved with the help of this Poincare inequality. And now the next step is to show that this implies an estimate for a slightly stronger integral involving also factors of h in here because of this relation here. So the corollary that we meet on our way to a sub-estimate for f sigma is the following. So if we assume that p is larger than m over n times 2 to the 8 times epsilon to the minus 6. So this is quite a bit larger now than in the previous lemma. And if we assume that sigma is less than n over 16 times epsilon cubed times p to the minus 1/2, so this is about half what's here, then we get that the integral of h to the m times f sigma to the p d mu over mnt or t is less than the same constant that we have up here. And so this is quite a bit larger. The point is that we made sigma even smaller and p very large. And the proof is quite simple. Observe that we can rewrite hm h to the power m times f sigma p. After all, this is a to the 2p, a 0 to the 2p divided by h to the 2 minus sigma to the power p times h to the m. And now let's put this down into the denominator, and then you get a 0 to the 2p divided by h to the 2 minus sigma minus m over p times p. But this can be written as f sigma dash to the power p, where sigma dash is equal to the old sigma just increased by m over p. But now the way we have chosen sigma and p, the sigma is less than n over 16 times epsilon cubed times p to the minus 1/2, and the m over p is less than exactly the same thing, the way I've set it up, m p to the minus 1/2 times n over m times epsilon cubed times 1 over 16 that follows from this assumption here, and then this together is less than n/8 times epsilon cubed times p to the minus 1/2. So this right. So making this assumption on p here, we get that this term, which goes like 1/p, can be easily absorbed into the term p to the minus 1/2, and therefore now f sigma dash p satisfies our LP estimate here, and therefore we could absorb this power h to m. It's just a different sigma. So if p is large enough, then this is just one of the LP norms that we've already uniformly bounded. Okay, now in the application, the m will be either n or 2. So this is not a parameter that's going to run. It's just either n or 2, and therefore this restriction on p here will be a restriction that only depends on the epsilon. And therefore, the restriction on the sigma itself will also ultimately only depend on the epsilon and on n. Okay, now with this lemma, we are ready to prove the superestimate. Now the superestimate for f sigma, which then proves this, of course, if we have a superestimate for f sigma, it shows this estimate here. So the superestimate will be obtained from the LP estimate in this corollary with the help of the Slampakia iteration and the Michael-Simon-Sobolev inequality. So the key ingredient here is the Michael-Simon-Sobolev inequality. And this says that given Mn contained in Rn plus 1, we have for u in W 1 of Mn, an inequality where integral of u to the n over n minus 1 mu Mn to the n minus 1 over n is less than a constant depending just on n times the integral of du plus another constant times, plus the mean curvature times u. And this in particular implies for n greater or equal than 2, you also get that the integral of u to the 2n or n minus 2 dmu to the n minus 2 over n is less than a constant depending on n times integral of du squared plus h squared u squared. And the key point here is that the geometry of the hypersurface only comes in through the mean curvature rather than the full second fundamental form. and the constant here only depends on n and not on the injectivity radius or any other geometric quantity. It's easy to get such inequalities if you allow the constant here to depend on the soup of the curvature of the manifold. But the main point is that the dependence on the geometry only comes in at the mean curvature level, the trace, and also only in an integral sense rather than in a soup estimate. Now, a similar formula in intrinsic geometry would typically not be true. Say, you cannot on a general Riemannian manifold replace this by the Riemann soup of the Riemann tensor. A torus, a thin torus would be an easy counterexample. And the proof here used the monotonicity formula for prescribed mean curvature surfaces in 1976 by Michael Simon. There is a new proof by the ABP maximum principle due to Simon Bentley. So there's a new proof. Optimal constant just recently by Simon Bentley. That's just a comment. Okay, so this is going to be an ingredient. The other ingredient, of course, has to be the evolution equation for the function f sigma that we've already developed earlier. So recall the evolution equation. Sigma, this was the following. We had ddt of f sigma was less than the Laplacian of f sigma, and then there was plus 2 times 1 minus sigma divided by h times the gradient of h times the gradient of f sigma. And then there was the good term, which we could estimate due to the convexity using this lemma that we have proved for this good term. Remember, there was this decomposition into the antisymmetric and symmetric part, and then we used the convexity to extract this good term from this quadratic gradient term. And then, of course, we had the bad term, a squared times f sigma. Now, when you now multiply with a cutoff function, sort of the measuring the bad part of the function, then this cross term can be absorbed in here in the diffusion term, and we have to somehow then control this bad term here. So now let k greater be 0 and set uk or fk to be the maximum of f sigma minus k and 0. And we choose k, in fact, be larger than the initial data of f0. in order to make sure that Fk initially is equal to 0. And we set the bed set AK to be the set of all x in Mn such that F sigma is bigger than k. So this is the set where this function Fk lives. And then we compute ddt of the integral of F sigma of Fk to the p d mu. So let p be greater or equal than 2 at least. And then do this computation. And now we compute as before, and then we estimate this from above, and then we get from here the integration by parts. We get again the p times p minus 1 times the integral of Fk to the p minus 2 times the gradient of Fk squared over Ak d mu. We throw away the time derivative of d mu, and we can absorb if p is sufficiently large, because this is quadratic. Yeah, maybe I'm too fast now. So this is minus epsilon squared times p integral f k to the p minus 1 times gradient h squared times 1 on h to the 2 minus sigma d mu. This is the term you get differentiating this. This is a p times f sigma a to the p minus 1 and so on. And then you insert this inequality. And then, of course, you get the cross term plus 2 times 1 minus sigma. That's 2 times 1 minus sigma times integral. And then you get 1 on h times f sigma or fk to the p minus 1 times gradient h times the gradient of f sigma. And then you get, of course, the bed term plus p times sigma. And now I estimate a squared by h squared, and then you get f sigma times fk to the p minus 1. Okay. And now if you choose again the p, since this is quadratic in p, and this is linear in p, and this term here, oops, there's a p missing, p times 2 times 1 minus sigma. So since this term is linear in p, this is linear in p, but this is quadratic in p. If we make the p huge compared to the epsilon, then these two terms together, the Schwarz inequality will absorb this one. So we end up for p again bigger than, say, 100 times epsilon to the minus 2, you get that ddt of integral fk to the p d mu is less than, say, minus 1/2 times p minus 1 integral fk to the p minus 2 gradient fk squared d mu. And then of k lives only on ak, so we can just, and outside ak this is equal to 0, so we can replace this by the whole manifold, and we throw away the remaining term from here. The cross term is gone, and then we just have left the term p times sigma times integral h squared f sigma times fk to the p minus 1 d mu. Yes. And now notice that on this set AK, we can estimate that the term 1/2 times p minus 1 times fk to the p minus 2 gradient fk squared. This can be estimated by the gradient of fk to the p over 2 squared. So if we choose a new function f to be fk to the p over 2, then we can write this slightly more elegantly. We get ddt of integral of, not f, I need a new letter, v. Let v be this, and this is just a square. So we get v squared d mu is less than minus integral gradient v squared d mu, or let's do plus here, and then this is less than, on the right hand side, sigma times p times the integral, and then now let's write this as h squared, and there's no point leaving the k here, so there's nothing you can gain by subtracting the h here, because you always have this factor f sigma, so we can just, I guess we just have to, this is the best really we can do. So this is sort of the key inequality we get. And now the idea is that we get integrals of this type here bounded if p is very large. So this is our chance now with the Sobolev inequality to get an iteration inequality going on the measure of the set AK and estimate the subnorm in terms of a very high LP norm. And these are exactly the integrals that we had bounded in the last lemma, in the last corollary. Okay, so now to do this, we have to apply the Sobolev inequality, the Michael-Simon-Sobolev inequality. Now, the Michael-Simon-Sobolev inequality has, of course, one bad term in there, so we have to see how to deal with this. So the Michael Simon. Sobolev. Equality implies that I can estimate the power 2q of, to the power 1 on q. And this q will be n over n minus 2 if n is greater than 2, and it will be just some number less than infinity if n equals 2. So I leave this as an exercise to deal with the case where n equals 2, but you can always write it like this, as you get this gradient v squared. This is exactly what we had, and then this was a constant depending only on n, and then we had the integral of h squared v squared. Now applying Hölder inequality, Hölder's inequality, I can estimate this by h to the n d mu, and then the power in the Hölder inequality was obviously n over 2 because it was an h squared term, so I get here 2 over n times, and then I get the power of v to the 2q, because this is exactly the corresponding exponent, and I get this to the power 1 over q. Because n minus 2 over n plus 2 over n is equal to 1. Okay? So using this, now I can use the fact, how do I estimate this guy here? Well, I can estimate that, and this is all over, because this was all over this v, this function v, lives only in AK, right? So the part of v is contained in AK. So I can make these integrals here all over the bad set. So then I can estimate integral h to the n over the bad set. And on the bad set, I just estimate this by f sigma to the power p, and then I get a 1 over, because on this set, f sigma k is bigger than k to the bigger than k, so I get an h a k in here, and I get the whole thing to the power 2 on n, which is less than k to the minus 2p over n times this integral here. But this integral here, if sigma is small, is bounded by this constant C2 that we had in the previous corollary, right? So this is exactly one of the integrals we estimated in the previous corollary. So we can write this as C2 to the power 2p over n if the sigma satisfies the assumptions together with p that we need. So if we need p bigger than 2 to the 8 times epsilon to the minus 6, and we needed that sigma was less than n over 16 times epsilon cubed times p to the minus 1/2. So then we get this estimate here. And now we estimate this term here from below by our improved LP estimate. So this is the higher power that we need on the left-hand side. So we get a good term on the left-hand side, and on the right-hand side, we have just things that are estimated with the help of the corollary. So, okay. All right, so yeah, let's do it slowly. Then we get from the inequality the integral integral v squared less than. So that was on the board just before. Now we know that initially this integral is equal to 0. So by integration up to t. So integrate this from 0 to t, then you get that the sup of integral v squared d mu mnt over the time interval up to some, let's see, up to where? Up to capital T, plus the double integral from 0 to t of the integral of v to the 2q d mu to the 1 on q over mn dt. Actually, there's of course a constant depending on n. Let's put this on the other side, this constant. So we get here a constant depending on n multiplied with sigma times p integral h squared times f sigma to the p d mu plus the constant that comes from here, which is k to the minus 2p over n times, oh no, this is nonsense what I'm saying here. You just get this terms here. Is this right? Yes. Why is that? Where did the bad term? Didn't explain this to the end. So we have this inequality here. This is, of course, also over the bad set. So we have this inequality here, and then here we have the same power as on the left. And this integral here satisfies this estimate. So if we make the k large enough, then with respect to C2, this power here, this whole thing will be less than, say, 1/2. So by making choosing k bigger than the maximum of k naught, which was the initial data of the p integral of f sigma, or the initial data of f sigma, and this constant here. So this is say 2 C2 times 1 over Cn, the Cn up here, which also goes in front. I was missing the Cn here. So by choosing this bigger than that, and let's call this K1. So if we only look at k's that are bigger than these constants, which only depend on the initial data. So here these are constants that we established just from the initial data. So if the k is bigger than that, then this whole extra term here has a factor times the thing on the left-hand side, which so we can absorb it on the left-hand side. So this thing is then estimated from below just by this integral, and therefore this justifies this inequality here. Okay. Provided, of course, k is bigger than k1. All k bigger than k1. Okay. Now we have to turn the two terms here. We have an integral of power of v, which is bigger than 2, which is good. And here we have the soup of an integral of v squared. So we have to now interpolate between this integral, this power, and this soup estimate of the L2 norm in order to get a space-time integral of a power of v, which is just a little bit bigger than 2, in order to get the Stampacchia iteration going. So now we use an interpolation inequality. It's actually a technique that works for many parabolic problems. Once you got to the stage, it all depends on whether you can handle the term on the right-hand side. So the interpolation inequality you use is that you can estimate an integral of 2q mod dv over the bad set to the 1 on q naught. If the q naught is between 1 and q, by the integral of v to the 2q diminished to the a over q times integral v squared diminished over ak, everything to the power 1 minus a, 1, where the a interpolates between the q and the q naught, so you get 1 on q naught is a over q plus 1 minus a over 1. And this can be done by choosing a equals 1 over q naught. And in this way, you have indeed that the q naught is a little bit smaller than the original q, which was bigger than 1. But the q naught is still strictly bigger than 1. So you give up a little bit of this power in order to create then an integral over space-time. So just using Hölder exercise, you get that the double integral from 0 to t over the base set ak of v to the slightly smaller power d mu dt to the 1 over q naught can be estimated by the left-hand side above, which you then estimate by Cn times sigma times p times the integral from 0 to t times the integral over ak of h to the power 2 times fk to the p, f sigma to the p, I'm sorry, f sigma to the p d mu. And now you can apply on the right-hand side and on the left-hand side the Hölder inequality to get an iteration inequality on the measure of ak here. And if you know the Stampacchia method, you know that we need to get a power of the measure of ak bigger than 1 in the end on the right-hand side. So this is achieved by taking a very high LP norm on the right-hand side. So now the rest is just Hölder's inequality. So now first the right-hand side can be estimated by this constant Cn times sigma times p times the space-time norm of the set ak to the power 1 minus 1 over r times the integral over space-time ak of h to the 2r times f sigma to the p times r d mu dt to the power 1 over r. And the space-time norm of ak is, of course, the integral from 0 to t integral over ak of 1 d mu dt. Okay. So you get this estimate, and now the now you apply the Hölder inequality on the left-hand side. From below, you get that on the left-hand side, the integral of over space-time ak. And now let's recall again what this was. Now we take v squared, and v squared was f k to the power p d mu dt, estimated by this was v squared. So now we go from v squared to v to the 2q naught. So we apply Hölder with q naught. So we get the right-hand side with an extra term. Right, so we get exactly this integral, and we get this right-hand side, which we estimate by this, but we get an extra factor coming from the space-time measure of ak. So we get the same constant Cn times sigma times p, but then we get the space-time measure of AK by this, with this power, 1 minus 1 over r, but also a power coming from here, which is another 1 minus 1 over Q naught. So this in total gives us a 2 minus 1 over r minus 1 over Q naught. And then we are left with this integral on the right. Times the integral 0 t integral k, which we now estimate brutally by all of mn times h to the 2r times f sigma to the p times r times d mu dt to the power 1 over r. Okay. Now, all that matters is that this exponent up here, this exponent has to be bigger than 1. Now, notice that Q naught is bigger than 1, just depending on n. So 2 minus 1 over Q naught is still bigger than 1. So depending on n. So we can now just choose r so huge that this exponent gamma is still bigger than 1. So can choose r depending just on on n, since Q naught is bigger than 1, and Q naught just depends on n. We can choose r of n such that 2 minus 1 over r minus 1 over Q naught equals gamma is strictly bigger than 1. Okay? So this So this fixes r. So this fixes the 2r equals n. This fixes 2r m, some integer fix the n, and then choose p and sigma to satisfy the assumptions of the corollary. Right? In the corollary, we had sort of h to the n, and we had something depending on this power here. So this is now sort of the p dash. So we choose sigma sufficiently small, depending on p. We choose p bigger than p times r, bigger than the number that depended just on epsilon and n, and we can satisfy all the assumptions of the corollary, and then this integral on the right-hand side is uniformly bounded. Then the bracket to the 1 on r is less than capital T to the 1 on r multiplied times C2, as in the corollary. C2 and we already know that because we are in the positive mean curvature case, we had already established an upper bound on capital T. So this is less than C3 since T is bounded. Okay, so now sigma is fixed, P is fixed, R is fixed, everything on the right-hand side is now bounded times the measure of AK to the appropriate power. So now we just check on the left-hand side, on the left-hand side, we may estimate that the integral from 0 to t, integral over ak of fk to the p d mu dt, this is obviously bigger on this set as the integral 0 to t of integral ak for if h is bigger than k, bigger than k1. So if we have now another, okay, then on this the set fk is bigger than, this gets smaller if I replace on this set let me think for a second. Let's do this slowly. So on this set, f, this is like f minus k to the p d mu dt on this set. And since this can be estimated by the set since the set is smaller ah, I can estimate this by f minus k to the p d dt, since the set ah is the smaller set. And then on this set, f is bigger than h, so I can estimate this. This is not absolute, I can estimate this by the integral from 0 to t integral ah times h minus k, because on the set h is less than f, right, to the p dt. But this is now a constant times the measure of ah, so I can write this as the norm of ah times h minus k to the p. So I end up with an inequality saying that h minus k to the p times the space-time norm of ah can be estimated by whatever is on the right-hand side. And that was now a constant, only depending on n times and epsilon, the p depending on n and epsilon, and the sigma also, and then this constant there depending on the constant c2, and this is multiplied by a k to the power gamma, where gamma is gamma of n bigger than 1. And this is exactly the iteration inequality that we know the lemma from Stampacchia, which tells us that then the measure, and this is true for all h bigger than k1. And k1 also only depended on the initial data, and this tells us that the measure of ak1 plus d is equal to 0, where d to the p can be estimated by the constant that was in front of our, there was a constant depending on gamma times the constant in front of the iteration inequality. So this is the, let's call this C4. So this is C4 to the T, C4 to the, no, this is C4 times, and then we get the measure of AK1 to the power gamma minus 1. But again, because the measure of the manifold is finite and the time interval is finite, this whole thing is dependent just on n and the initial data. And this, of course, gives us the suit bound, because if this measure is 0, it must mean that the function must be less than k1 plus d, and d satisfies the a priori estimate there. So we get the suit of f sigma on 0 t cross mn less than k1 plus d. And this is completing the proof of the pinching estimate. Okay. All right, so if you want a reference for this thing here, there's a very nice presentation of these iteration inequalities due to Stampacchia in the book by Kinderlehrer Stampacchia. It's the chapter on Hölder regularity. There's only one book by Kinderlehrer and Stampacchia. There's some variation on inequalities in the title. Right. I think the key thing to remember is you need the Poincare inequality, you need the Michael-Simon-Sobolev inequality, and you need Stampacchia iteration. So you don't get away with the maximum principle. You need the full power of the diffusion term. The diffusion term gives you this extra grade, this good gradient term. And because for these submanifolds, you have this wonderful Michael-Simon-Sobolev inequality, you can convert this good gradient term coming from the diffusion and from the Poincare inequality, you can transform that into a higher power of the function you want to estimate and set up the Stampacchia iteration. Okay. Now, once we have the pinching estimate, it essentially means that at the C0, at the C2 level, at the curvature level, the surfaces want to become sort of spherical in terms of the curvatures. The curvatures want to be together, and that looks like it wants to be a sphere whenever the curvature is huge. But at the moment, it could still happen that at just one point of the manifold, the curvature gets huge, and the eigenvalues of the second fundamental form are close together at that point. But does that mean the whole manifold has to look like a sphere? It's not clear. So you would like to know that if this happens, it happens in a big neighborhood. And if the neighborhood is really big, then the eigenvalues will be the same everywhere on the manifold. It will cover the whole manifold, and then it will be around tiny, tiny sphere shrinking to a point as the curvature goes to infinity. So now we have to add in a gradient estimate for the curvature that tells us if the curvature gets huge somewhere, it will be huge in a whole big neighborhood. Now, in general, this would not be true, but we have to exploit in getting the gradient estimate, the pinching estimate for the curvature that we have just established. So the next step is use the pinching estimate to get a gradient estimate. Now, this should be familiar from just PDE theory. You have some estimate on the lower order quantity. You want to now differentiate through and get an estimate on the next higher order quantity. Turns out that does work in this setting as well. Now, the theorem is the following. If Mn0 is as above, so in particular, the pinching estimate holds that we've just established, then the following is true. Then for any eta, there exists a C eta, which is depending on the initial data, in particular on the estimates that and the constants that we just used in the pinching estimate, such that the gradient of the mean curvature squared is less than eta times the mean curvature to the power 4 plus C of eta. Is that right? Yeah. Now, why is that a good estimate? Our last estimate had something like, if you think of the last estimate, we would have something like gradient h squared less than a constant times h to the 4 minus sigma in order to break the scaling invariance. See, h to the 4 scales exactly like gradient h squared. So you want to do something which is better than the scaling. Now, it turns out it's enough to do it this way because the constant eta can be arbitrarily small, and this constant here is just an absolute constant. It will go away if you rescale. It will be very small compared to this term. So that is enough breaking of the scaling invariance to prove what we want to prove. Now, the proof idea maybe this is something I do not carry out because it goes back to the maximum principle again. Well, you just have to compute from the evolution equation of the mean curvature, which was Laplacian of h plus h times a squared. You compute that ddt of gradient of h squared, but this is something like Laplacian of gradient h squared minus the Bochner term. This comes from computing the Laplacian of a square. You get 2 times what you get from the time derivative of gradient h times gradient h, but from the cross term you get this term. And then you get, of course, the terms that come from this reaction term, and also here you have to exchange the Laplacian of the gradient with the gradient of the Laplacian, so you get some curvature terms there as well. So you get gradient of curvature coming in, and it's easy to see that what you get is some constant depending on n times the mean curvature squared times the gradient of the full second fundamental form. Let me see here, what do we get? Why don't I just write it down exactly what you get, and then you can see you get exactly plus 4a squared gradient h squared and plus 2 times gradient IH times HMJ multiplied with gradient JH times gradient IHN. This with, yeah, this looks right with the indices, and then there is a term plus 2H times gradient IH gradient IA squared. So this last term obviously comes from the gradient of H, 2 times the gradient of H multiplied with the gradient of this term here, yes, and this one comes from when the gradient falls on that, and this has to do with the fact that we exchanged the Laplacian of the gradient with the gradient of the Laplacian. The point is that this whole thing can be estimated by the Laplacian of gradient h squared minus 2 times the Hessian of h squared plus 4a squared gradient h squared plus, and let's just write this term there, 2h times gradient IH gradient I squared, and this is an upper bound. So now the problem is, of course, that we do not have now a curvature bound. We don't know that a squared is bounded. And similarly here, this term has sort of a similar order, but it has in fact one factor which involves the full gradient of the second fundamental form. So it's not just the gradient of the mean curvature. So we really have here one term involving the full gradient of the second fundamental form. But the real bad part is that everything is multiplied with curvature, and curvature can blow up. So it's definitely not something that has a definite a priori estimate. We just want it to be nice compared to the scale of curvature. So now the trick is to add something in that is able to cancel a bad term like this. Now, we have just estimated the trace-free part of the second fundamental form. So the idea is to add something in that involves this trace-free part of the second fundamental form. So idea, add in a term involving the trace-free part of the second fundamental form. We just had a good estimate on this. Now, let's see, if we take ddt of the trace-free part of the second fundamental form, let's write it out, that's this term. And going back to the old evolution equations that I wrote down for you 2 lectures ago, you see And this is the Laplacian of the trace-free part of the second fundamental form. And then there is a Bochner term, which is the gradient part here. And then you pay with a term which looks like 2 times a squared times exactly this term. Now the idea is that this gives you a good term here, and you pay for this good term only with a bad term which has a very good estimate. That's our pinching estimate. Right? The bad term has the pinching estimate, so it's not so bad. Now, the problem why this doesn't work immediately is that the problem here is that this term here doesn't scale quite right. So this has a gradient a squared, whereas this has sort of a gradient a squared times curvature squared. Now it turns out that if I multiply this one with h squared, I get many bad cross terms. And if I then add this in, I have so many bad cross terms that it's not clear how I use it. So it turns out the following combination of terms works best. You have to take sort of a bean approach. So take the following combination works. So you take a function f, you take gradient h squared divided by h. So you reduce sort of the scaling by one factor. This gets rid of one of the 2 powers of a squared in this equation. And then on the other hand, you have to multiply this by h. So you take a lot of n times h times a squared minus 1 on n h squared. Now this scales exactly the same way as that one. And then you add enough of some constant times a squared, and then you add, you subtract some eta times h to the cubed. So this is a lower order term, and this combination does it. So the point is you can apply the maximum principle to f. And namely you get, maybe I'll show you a step on the way. You do the calculation and you come up as an intermediate step that you can estimate f. But the recipe is the same. You compute ddt of f, you bring everything into the form on the right-hand side, Laplace f plus the rest, you collect the rest, and what you get here is the rest looks like a squared gradient h squared over h. So this is a bad term. Then you get 2 divided this is again a bad term. Then you get a bad term here, h gradient h squared. There's a tiny eta in front. And then you get a good term minus n times 2 n minus 1 over 3n times h gradient h squared. And then you get a bad term 2n c3 times a to the 4, and a bad term 3n a squared times h times trace 3 part. And then you get a good term minus 3 eta a squared times h cubed. And I should tell you that here I used the of course the evolution equation for gradient h squared and the evolution equation for a squared minus 1 on h squared, as I told you. Now, this term here leads to the bad term there, right? So this is the worst term on the right-hand side you get is this one here. And the point is that this bad term, which scales like h to the 5, can be absorbed by this tiny good term, which also scales like h to the 5, because this here satisfies the pinching estimate. So this is a power by the pinching estimate slightly less than h squared. Remember, it was h to the 2 minus sigma. So in reality, because a squared is less than h squared, this is less than a constant times h to the 2 minus sigma. And this, on the other hand, because a squared is bigger than 1 on n h squared, this is a fixed constant eta times h to the 5. So since the n will only depend on little n, because we just have to absorb the bad gradient terms into this term here, we just have to make the n large enough that this gradient term absorbs the two bad terms coming from the gradient here. Notice this is the whole gradient, not just a little bit. Since this, these two are absurd, and similarly here, this one here is just the f times a squared. So these two terms will determine n, and then these two terms, this bad term can be absorbed in this because of the pinching estimate. Maybe I write part of that down. So can choose n equals n of little n to absorb gradient terms, then use that 3n times a squared times h times a squared minus 1 on n. H squared is less than a constant depending just on n and the initial data, the pinching estimate, times h to the 3, h to the 5 minus sigma. And by Young's inequality, I can estimate this by 1 on n times eta times h cubed, which I get from here I get even 3 on n times h to the 5, sorry, h to the 5, of course, plus something, a constant depending on n, mn0, and sigma, yes, a huge constant. So this completely absorbs this term in there, and you right, and this tells you that ddt of f is less than Laplace f plus some constant depending on n, and sorry, this constant of course also depends on eta, right? Because I put an eta in front of here. This constant will depend on something like eta to the -1, right? So here there will be a constant depending on the initial data and on eta, of course, and on the sigma. But sigma dependent on the initial data. Yeah. So you get this, and this is just linear in time, but this means that f can grow at most linearly in time beyond its initial data. So this says that f is less than the sup of f on the initial data plus c times t by the standard maximum principle again, right? You subtract c times t, and then this term gets cancelled, and you apply the maximum principle to f minus c times t. And this, of course, implies the desired estimate, because then you get gradient h squared is less than, let's call this C5. You get that this is less than C5 times h plus eta times h to the 4, and this can be estimated by 2 eta times h to the 4 plus c6, and c6 depends on eta and on these other constants. And of course this is good enough because eta is arbitrarily, so we have this arbitrarily small constant in front of h to the 4 plus a constant depending on eta and the initial data. Okay, here's a challenge. This is the original proof in my original paper. I think you can do the estimate somewhat better by using an inequality that, yeah, let me see. Did I use this here? Let me see. Let's check. I think I may have used. There's one thing I didn't tell you. Yeah, there's something I did not tell you here. What you also had to use in establishing that you got this good term here. That's two, I didn't explain this term here to you. Right? Where does this come from? It comes from this gradient term. So this is one thing I didn't explain. So let me explain that. It would be unfair not to explain that. The term gradient a squared minus 1 on n gradient h squared for n greater or equal than 2 can be estimated from below. Right, because it's obviously greater or equal to 0 because this is a trace than that. So for any such matrix, you have this non-negative, that's clear by just Schwarz inequality. But for n greater or equal than 2, this can be estimated from below. And that gives us an extra good term, which is on the blackboard here. Okay, and this is the following lemma. It's nothing to do with evolution equations. It just says that on any hypersurface, we have that gradient a squared is bigger than 3 over n plus 2 times gradient a squared. Now, and now obviously for n equals 1, this is trivial because then 3 over 3 is 1 and there's only one curvature, so it's a trivial inequality. But for n bigger than 2, this is interesting because 3 over n plus 2 is bigger than 1 on n for n greater than 2. In fact, 3 over n plus 2 minus 1 on n is equal to n plus 2 n times, what do we get? We get 3n minus n plus 2 is equal 2 times 2n minus 2 is 2 times n minus 1 over n plus 2 times n. Okay. And this implies that the difference that this term here is actually a fixed positive constant bigger than gradient a squared, giving the good term here. And the proof of the lemma uses the fact that you can decompose the second fundamental form into its irreducible parts. So you can write gradient I hjk as eijk plus fijk. And you can do it in such a way that the f is completely trace-free and the e contains all the traces. In fact, you can check that eijk, and of course this uses the fact that all the traces of E are the same by the Kodazzi equations. This is totally symmetric, so all the traces are the same, and they are of course some multiple of the gradient of H, and therefore you have to can write this as gradient IH GJK plus gradient JH GIK plus gradient KH GIJ. you check that this guy has exactly all the same traces as this, and therefore this one is trace free. And if you multiply it with this guy, then it's 0, because this is all these terms are taking traces. So these E and F are orthogonal to each other, so we can use Pythagoras. So it must be true that gradient A squared, the left-hand side, is bigger than any of these components. So it's bigger than E squared. And E squared has just to do with the gradient of H squared, and you just compute. This is 3 over n plus 2 times gradient. And that completes the proof of the lemma and justifies this good term on the right-hand side of the evolution equation. Okay, now I was talking about the challenge, and the challenge is instead of using Young's inequality here to absorb this term, you should be able to actually do this with a slightly smaller power here, using our precise estimate and then getting an estimate in terms of a smaller power. So the challenge show that a stronger estimate is true namely gradient H squared is less than some constant C7 times H to the 4 minus sigma, maybe plus some constant C8. In other words, instead of having eta times H to the 4, you should also be able to get just a constant times H to the 4 minus sigma. And since H is bounded from below, you should even be able to drop this term and just get this estimate, which sort of beautifully fits with the other pinching estimate. Now that's the gradient estimate. And from the gradient estimate, it's now easy to see that there's some work that the whole theorem can be proved. But that's, I think, for the next lecture. So see you next time.